I want you to stop whatever you're doing for just a second. Like really, just look down at the floor.
Or the pavement, or, the grass beneath your feet if you're outside.
Right, exactly. Because we walk around every single day with this fundamental assumption that the ground is just, well, that it's just there.
Yeah, that it's solid and static.
Totally. Dependable. Like
Yeah.
it's the foundation of absolutely everything. But I want you to imagine taking an elevator straight down from wherever you are standing right now.
And not just, a few floors down into a basement.
No, not a mine shaft either. I want you to imagine dropping 400 miles straight down into the earth.
Which is about 640 kilometers down.
Yeah. And at that depth, the reality of the planet you live on becomes completely, entirely alien.
It really does.
The rock down there is being crushed by pressures that are so unfathomable. I think it's around 23,000 bars, right?
Roughly.
Yeah. So if you somehow manage to build a machine out of like the strongest alloys known to human engineering and you put it down there, it wouldn't just get crushed.
No, it would be fundamentally transformed.
Right. The atomic structure of the metal would just be altered entirely. And yet this totally alien environment is directly responsible for every earthquake, every volcanic eruption, and every mountain range that has ever shaped the surface world that you actually inhabit.
It's crazy to think about because the human brain honestly just struggles to conceptualize the environment at that depth.
Oh, for sure.
Like we instinctively categorize materials as either solid or liquid. A rock is solid, magma is liquid. That's how we are taught.
Right.
But when you descend 400 miles into the Earth's interior,
Mm.
you enter this domain defined by something called rheological duality.
Okay, wait. Rheological duality. Let's not let that slip by without unpacking it.
Sure.
Rheology is basically the study of how things flow, right?
Yeah.
But you just said the rock down there is a solid crystal being crushed. So, I mean, how can a solid crystal flow?
I know, it sounds like a total contradiction. But it depends entirely on the time frame that you are observing.
Okay, what do you mean by time frame?
Well, if you look at this deep rock through the lens of a high-frequency seismic wave like, say, the shock wave from a sudden violent earthquake, the rock behaves exactly like a rigid ringing bell.
Oh, wow.
Yeah, it is absolutely solid in that moment. It snaps, it fractures under sudden stress, and it transmits those sharp acoustic waves beautifully.
Right, because it's a rock.
Right. But if you change your perspective and watch that exact same rock over geological time, like over millions of years, it behaves like a highly viscous fluid.
So wait, it's kind of like silly putty.
Oh, that's a great comparison.
Like if you hit a ball of silly putty with a hammer, it shatters like glass, right? It just breaks into pieces.
Yeah.
But if you just leave that same ball of silly putty on a table for a week, it slowly melts into this flat puddle.
That is a brilliant way to picture it, actually. The mantle is this solid crystal that is churning and convecting and flowing at a rate of just a few centimeters per year.
Just a few centimeters.
It is literally a slow-motion ocean of solid rock. And this dual behavior, being solid but flowing, is the driving mechanism of a continuous cycle that has been operating inside our planet for 4.5 billion years.
Which brings us perfectly to our mission for this deep dive. Because today, we are going to explore this specific, bizarre underworld.
We really are.
We are zooming in on a layer of the Earth known as the Mantle Transition Zone, or the MTZ, as we'll probably call it.
Yeah.
And this is the realm starting at roughly 410 kilometers down and ending at 660 kilometers down.
Yeah, this zone is basically the tectonic engine room of the whole planet.
The engine room, I love that. And the source materials we are pulling from today, they give us this unprecedented look at the machinery inside that room.
They absolutely do. I mean, we have access to incredible new research from literally just the past year or two.
We really do. It's wild. We have a stack of sources today that frankly read like science fiction, but they are very, very real.
Yeah.
We're going to examine the crushing crystallographic phase transformations of a really common mineral. We are going to look at a 2025 study where scientists managed to map the subterranean architecture of the United States. And they did it without using earthquakes, which is
a huge deal.
Yeah, they used the ambient hum of ocean waves, which I still barely understand, but we'll get into it.
We definitely will.
We also have research on this incredibly rare diamond pulled out of a mine in Botswana that holds proof of massive hidden oceans.
Right, oceans of water, but not the way you think.
Exactly. And finally, we're going to dive into the geodynamic trapdoors that literally hold back avalanches of solid rock deep within the mantle.
Getting a grasp on these concepts, it just fundamentally shifts your entire perspective.
It really does.
You realize that the continents we build our cities on, the ground we walk on, it's really just this thin, brittle scum floating on top of a hyperactive thermodynamic engine.
Brittle scum. That's reassuring. But, okay, let's start taking this engine apart, piece by piece.
Sounds good.
We need to set the scene for this mantle transition zone first. So we defined the boundaries. 410 kilometers at the top, 660 kilometers at the bottom.
Right.
But what exactly dictates where those boundaries even are? Like, why isn't it just a smooth, gradual gradient all the way down to the core?
Well, the boundaries are dictated by the physical limits of atomic architecture.
Okay, atomic architecture.
Yeah. To understand this, you really have to look at the dominant ingredient of the upper mantle, and that is a mineral called olivine.
Olivine.
Right. Now, anyone who has ever looked at the gemstone peridot, that bright olive green stone.
Oh, yeah, the August birthstone, I think.
Exactly. If you've seen peridot, you have seen gem-quality olivine. It is incredibly abundant. It makes up roughly 70% of the Earth's upper mantle.
Okay, so if I'm taking my imaginary elevator down past the crust, the walls outside are essentially just an endless, crushing sea of hot green crystal.
Mostly, yes. But as your elevator goes deeper and deeper, the sheer weight of the hundreds of miles of rock above you, it increases the pressure exponentially.
Naturally.
And when you hit exactly 410 kilometers deep, which is a threshold seismologists refer to as the D410 boundary, the pressure reaches about 14 gigapascals.
Okay, I can't even begin to visualize a gigapascal. What does 14 of those actually feel like?
Well, consider the deepest part of the ocean on Earth, right? The Mariana Trench.
Right, which is already terrifyingly deep.
Exactly. The pressure down there is about 1,000 times standard atmospheric pressure. But at 14 gigapascals, you are dealing with pressure that is roughly 140,000 times atmospheric pressure.
Oh my God.
Yeah. And at that exact threshold, the physical architecture of the olivine crystal simply cannot sustain itself anymore.
So what happens? Does the pressure physically break the crystal?
It doesn't break it into pieces, no. It actually forces the atoms to completely rearrange themselves to take up less space. See, olivine normally has an orthorhombic crystal structure.
Let's pause on that word. Orthorhombic. What does that actually mean for the shape of the molecule?
Imagine a three-dimensional grid, kind of like a brick.
Okay.
An orthorhombic lattice has three axes that all intersect at 90-degree angles, just like a standard rectangular brick. But all three of those axes are different lengths.
Got it. So it's very organized.
It is an organized structure, yeah. But under 14 gigapascals of pressure, there is just too much empty space between the atoms in that specific arrangement.
Too much empty space.
Right. The atoms are being squeezed so hard that the lattice actually collapses. It just snaps into a much tighter, denser configuration called modified spinel structure.
Wow.
And we call this new, dense mineral wadsleyite.
Wadsleyite. Okay, I always try to find a tactile analogy for this kind of stuff.
Please do.
Is this akin to taking like a fluffy square piece of white bread and you just crush it in your fist until it becomes a dense, heavy little dough ball?
Yeah, that's exactly it.
Like the ingredients haven't changed at all. It's still the same flour, water, and yeast, but the architecture is fundamentally altered, making it way heavier and denser in a smaller space.
That bread dough analogy works perfectly for the concept of density. The chemical formula is identical. It is still magnesium, iron, silicon, and oxygen.
Right.
Not a single atom is added or removed, but they are packed together with extreme efficiency. Now, here is the really crucial part for the surface of the Earth.
Okay.
This specific phase transition, this collapse from olivine into wadsleyite, is exothermic.
Exothermic, meaning it releases heat.
Yes.
Wait, that actually really confuses me.
How so?
Well, if you were taking something and crushing it into a denser solid, how does it release heat without just melting itself? Like, wouldn't a massive heat release turn that dough ball into a liquid magma?
That is a very logical assumption to make, but you have to factor in the immense heat capacity of the mantle and, of course, the extreme pressure.
Ah, the pressure keeps it solid.
Exactly. The heat released by the atomic rearrangement is significant, absolutely.
Right.
but it's not nearly enough to overcome that crushing pressure that forces the rock to remain a solid.
I see.
So the ambient temperature of the rock rises slightly, but it stays strictly crystalline, and the fact that it releases heat has massive, massive thermodynamic consequences.
What kind of consequences?
It creates what physicists call a positive Clapeyron slope.
A positive Clapeyron slope. Okay, I definitely need you to translate that into English. Why does a slope matter down there?
Well, let's look at the basic rules of thermodynamics. Because the transition from olivine to wadsleyite releases heat, the reaction inherently prefers a colder environment.
Right.
It is much, much easier for the crystal lattice to collapse and dump its excess heat if the surrounding rock is already cold.
Okay, yeah, I follow that. A hot room doesn't want more heat, but a cold room will gladly take it.
Exactly. So picture a tectonic plate at the surface of the Earth. It's made of cold, dense ocean floor. At a subduction zone, this cold plate dives down and begins sinking into the hot mantle.
Like a cold slab of ice sinking into a warm bath.
Precisely. Now, because that sinking slab is thousands of degrees colder than the deep mantle rock surrounding it, the olivine inside that specific slab hits the ideal thermodynamic conditions to collapse into wadsleyite much earlier.
Oh.
It doesn't need to reach 410 kilometers of pressure. Because it's so incredibly cold, it might collapse at, say, 390 kilometers depth.
Ah, that makes so much sense. So the
Mhm.
transition line isn't just perfectly flat across the Earth?
Not at all.
While the normal warm mantle transitions at 410, the cold sinking tectonic plate transitions at a shallower depth.
Yes. And remember your bread dough analogy.
Right, it's denser.
Right. Wadsleyite is significantly denser and heavier than the olivine around it.
Yeah.
So you suddenly have this localized, massive chunk of ultra-dense wadsleyite sitting higher up in the mantle than it normally would be.
Because it transitioned early.
Exactly. And gravity takes hold of this dense mass, creating a powerful downward pull. It acts as an active gravitational accelerator.
Oh, wow.
The heavy phase transition is literally yanking the rest of the tectonic plate down into the Earth with it.
That is a profound realization, honestly.
Like, really is. Yeah.
Like, the reason the continents are drifting apart, the reason the Pacific plate is diving under Japan and creating these massive earthquakes, it's all being driven by the specific way this tiny green crystal chooses to collapse and release heat 400 miles down.
Yep.
If olivine didn't have this exact positive Clapeyron slope, plate tectonics might just not work.
It really highlights the ultimate butterfly effect of geology. The microscopic behavior of atoms directly dictates the macro drift of entire continents.
That's just wild to think about.
And, that is only the top boundary of our transition zone. As you continue to drop deeper, the pressure just keeps climbing.
Right, because there's more rock above you.
Exactly.
Hmm.
And when you reach roughly 520 kilometers deep, that wadsleyite dough ball gets crushed a second time.
Wait, it can get even denser.
Oh, yes. At 520 kilometers, it is forced to abandon that modified spinal structure and adopt a true cubic spinal structure.
Okay.
And this new mineral phase is called ringwoodite.
So just to track this, olivine to wadsleyite at 410, and then wadsleyite to ringwoodite at 520.
Correct. And the transition at that D520 boundary is also exothermic, so it operates on very similar thermodynamic principles, although the jump in density isn't quite as dramatic as the first one at 410.
Okay, let me play skeptic for a second here.
Go for it.
We have these very neat theoretical layers drawn on a chalkboard, right? Olivine at the top, wadsleyite in the middle, ringwoodite at the bottom.
Yeah.
But no human has ever actually been down there. We can't drill to 400 miles. I mean, the deepest hole ever excavated by humanity is the Kola super deep borehole in Russia. And they barely scraped past 7 miles down before the drill bits literally started melting.
That's right.
So how do we actually know these specific boundaries exist at exactly 410 and 520 kilometers? Like, if we can't see them or touch them, how are we drawing a map of this?
Well, we basically use the Earth as its own diagnostic tool. We rely on seismology.
Okay.
Historically, whenever a massive earthquake occurs, it releases a tremendous amount of energy in the form of seismic shock waves, and those travel entirely through the planet.
Right.
As those acoustic waves travel downward, they eventually hit these sudden jumps in density, these phase boundaries we just talked about.
And what happens when a wave hits a denser rock?
When a wave hits a denser layer, some of the energy refracts, but some of it bounces back up to the surface as an echo.
Oh. So it's essentially like a planetary sonogram.
That's the classic method, yeah. By measuring the exact time it takes for those deep echoes to reach different seismometers on the surface, scientists can mathematically reconstruct the depth and shape of the boundaries.
That makes sense.
But this traditional method has always suffered from a severe limitation, particularly when trying to map that middle boundary, the 520-kilometer mark.
Why is the 520 harder to see than the 410?
Because the transition from wadsleyite to ringwoodite isn't a razor-sharp line. It is a somewhat gradual phase change. The density increases over a span of several kilometers rather than all at once. And because the boundary is fuzzy, the seismic waves don't bounce off it cleanly. The returning echo is incredibly faint.
I imagine it's kind of like trying to see your reflection in a super foggy bathroom mirror versus, a perfectly polished piece of silver. The signal is just scattered.
That's a great way to put it. Furthermore, the traditional method relies on waiting for a massive earthquake to happen, just to generate a loud enough ping to see anything at all.
And you can't predict those.
Exactly. Earthquakes are unpredictable, and they only happen along specific fault lines. So our historical maps of the deep Earth were heavily biased.
Because we only had data from where the earthquakes were.
Right. We had decent pictures beneath active fault zones, but huge blurry blind spots beneath stable continents where earthquakes are super rare.
Which perfectly sets up this 2025 study in our source stack by Eamon and colleagues.
Yes, it does.
Because they managed to map this incredibly elusive, blurry 520-kilometer boundary across the entire contiguous United States.
They did.
And they did it without using a single earthquake, which is just wild to me.
The methodology they employed is just a testament to how far computational geophysics has come in recent years. Since they couldn't rely on the loud, directed ping of an earthquake, they turned to something called ambient seismic noise correlations.
Ambient seismic noise. Okay, I hear the word noise and I immediately think of static on a radio. What is making ambient noise inside the Earth?
Actually, it's the surface of the planet itself.
The surface?
Yeah. Every second of every day, the environment is hammering the crust. Ocean waves are endlessly crashing against the continental shelves.
Yeah.
Massive atmospheric pressure systems, like storms, weather fronts, they're dragging across the landmass. Even the wind howling against mountains transfers kinetic energy into the ground.
Oh, wow.
All of this surface chaos creates a continuous, very faint, ultra-low frequency hum. The Earth is constantly vibrating.
Wait, I really need to make sure I understand this.
Sure.
So instead of using a directed, powerful sonogram burst like an earthquake to map the deep interior, they are trying to map the structure of a giant office building just by standing inside and listening to the ambient rumble of city traffic outside the walls.
That is exactly what they are doing, and the complexity of the math required to do this is just staggering.
I can't even imagine.
They took continuous data recordings from thousands of seismic stations scattered all across the U.S. arrays, like the famous U.S. Array project.
Okay.
And by taking years of this random background hum and running massive computational cross-correlations, they essentially filtered out the chaos.
So they just cleaned up the static.
Yeah, they isolated specific frequencies, primarily in the 3 to 10 second period band, which corresponds to roughly 0.1 to 0.3 hertz.
That is very low frequency.
Very low.
Yeah.
But in that specific low-frequency hum, they could detect the infinitesimally faint echoes of the ambient noise bouncing off the deep mantle boundaries.
That is genuinely mind-blowing. Pulling a map of the deep Earth out of the sound of ocean waves crashing on the coast.
It's beautiful science.
So when they finally cleared away all the static, what did this ambient sonogram actually reveal about the mantle beneath the United States?
Well, it revealed that the mantle transition zone is anything but a flat, uniform series of lines.
Oh, really?
Yeah, it is intensely topographical. The researchers described it as having a highly complex, step-like arrangement.
Step-like, meaning the depths of these boundaries, the 410, the 520, are physically changing depending on which state you are standing in.
Radically changing. Let's look at the western United States for a second. Places like California, Nevada, and the Pacific Northwest. Beneath the West, the mapping showed that all the transition boundaries are significantly depressed. They sit at much greater depths than the global average.
Okay, let's test my memory on the thermodynamics here.
Let's hear it.
You said the transition to wadsleyite is exothermic. It has a positive Clapeyron slope, meaning it prefers cold.
Yep.
So if the boundary in the west is pushed deeper, it requires more pressure to force the transition.
Wow.
That implies the rock there is too hot to transition at the normal depth, right?
You absolutely nailed it.
Yes.
The mantle beneath the western U.S. is experiencing elevated temperatures. likely due to active thermal upwelling from deeper in the mantle.
Wow.
Because it is unusually hot, the olivine needs extra pressure to force the atomic collapse,
Yeah.
pushing the D410 boundary deeper into the Earth.
You know, that tracks perfectly with the surface geology. The West is full of geothermal activity, right? Yellowstone, the Cascades.
Exactly.
But what did the map show when they looked at the central and eastern U.S.?
Basically, the complete opposite scenario.
Right.
Yeah. Beneath the stable, ancient cratonic interior of the U.S., so the Midwest and the East Coast, the transition zone is massively thickened. The boundaries are pulled upward toward the surface.
Okay, so it's cold.
Very cold.
Yeah.
And the reason for this is honestly one of the most haunting discoveries in geology. This thickened zone is essentially a massive geological graveyard.
A graveyard. What on earth is buried under the Midwest?
The cold, dense, stalled remnants of the ancient Farallon slab.
The Farallon plate. Okay, I know a little bit about this. It was this colossal oceanic tectonic plate that existed in the Pacific Ocean millions of years ago, right?
Yes.
And it got pushed eastward, subducting entirely under the North American continent.
Right. The entire tectonic plate slid beneath North America. And for decades, scientists suspected that a plate that massive wouldn't just melt away and disappear immediately.
It has to go somewhere.
Exactly. And this ambient noise mapping provided the smoking gun. The cold, dead corpse of this ancient oceanic plate is still down there.
Just sitting there.
It is just sitting in the transition zone beneath the central U.S. And because it is a massive slab of cold rock, it chills the surrounding mantle, altering the Clapeyron slope and pulling the phase boundaries upward.
It is so strange to think about. Like, millions of people in the Midwest are just walking around, going to the grocery store, completely unaware that 400 miles beneath them is the ghost of a dead ocean plate.
And this graveyard is not completely dormant either.
What do you mean?
It is actively affecting the modern geology above it. For instance, the mapping revealed a very localized, pronounced thinning of the transition zone right beneath the Rio Grande Rift, which runs through New Mexico and Colorado.
Okay, well, if a thickened zone means cold, then a thin zone means heat.
Correct. The leading hypothesis right now is that fragments of that dead Farallon slab are finally beginning to heat up after millions of years.
Oh, wow.
And as they heat up, they release volatile fluids that were trapped inside the rock, mostly water and carbon dioxide.
And those fluids go up.
Yes. These hot, buoyant fluids are migrating upward from the transition zone, creating a localized hotspot that thins the boundaries and actively drives the rifting, the physical tearing apart of the crust at the surface in New Mexico.
I just love how interconnected all of this is. A dead slab 400 miles down sweats out some hot fluid, and a mountain range tears apart on the surface.
It's all one big system.
Now, I saw one other detail in the Amen study that really confused me. They mentioned that in the southwest U.S., the 520-kilometer boundary wasn't just one echo. It split into two distinct reflectors.
Yeah.
Did the wadsleyite transition just get confused and happen twice? Like, how do you get two echoes?
Not exactly. Wadsleyite still turns into ringwoodite at the normal depth.
Yeah.
But this split boundary is a chemical fingerprint of something else entirely.
Okay.
When an oceanic plate, like the Farallon subducts, it isn't just made of olivine, it carries a thick layer of basalt on top of it.
Basalt being the dark, heavy rock that makes up the actual ocean floor crust, right?
Exactly. And basalt is chemically very different from olivine. It is extremely rich in calcium.
Okay, so we are dragging a bunch of calcium down into the pressure cooker.
Right. And when calcium-rich basalt reaches these extreme pressures, it undergoes its own unique phase transition.
Oh.
The minerals in the basalt transform into a dense structure called calcium perovskite, near 18 gigapascals, which happens to sit right in the middle of the transition zone.
I see. So the first echo they mapped is the standard wadsleyite to ringwoodite transition happening in the bulk of the mantle.
Yes.
And that second echo, sitting just a little bit deeper, is the calcium perovskite transition happening specifically within the chunks of the ancient ocean floor.
Exactly. It's a double echo effect. It is literal, physical, seismic proof that surface crust has been dragged all the way down into the deep mantle and hasn't completely mixed in yet.
That is fascinating.
And there is one more crucial finding from this study that we absolutely must discuss.
What's that?
The researchers noted that if the rock in the transition zone contains even 1% water, the seismic boundary at 520 kilometers becomes 3 times sharper and more reflective.
3 times sharper. So the fact that their ambient noise mapping was able to see it so clearly strongly implies that the rock down there is wet.
It heavily hints at it. The mathematical models align perfectly with the presence of hydration.
But
But In the physical sciences, a strong seismic hint is still circumstantial evidence.
Right.
You could build all the computer models you want, and you could listen to all the echoes, but to definitively prove that water exists 400 miles down, you need a physical sample. You need to hold a piece of the transition zone in a laboratory.
Which poses an obvious, basically insurmountable problem. We just established that we cannot drill down there. We can't send a robotic probe. The pressure would just vaporize it.
Exactly.
So how in the world do you get a rock from 400 miles deep all the way up to a laboratory bench? The answer is you don't go get it. You let the Earth bring it up to you.
Yes, you do.
And the vehicle the planet uses to deliver this deep mantle mail is a diamond.
It's true. Diamonds are arguably the most valuable scientific tools on the planet.
Yeah.
And not for their sparkle, but because they are the ultimate chemical time capsules.
How so?
Well, a diamond is an incredibly strong, tightly interlocked lattice of carbon atoms. But more importantly, it is chemically inert. It does not react with the surrounding environment.
So if a diamond is forming deep inside the Earth and it accidentally swallows a tiny speck of the surrounding rock-like, an inclusion while it's crystallizing, that speck is hermetically sealed.
Exactly.
It is locked inside an impenetrable carbon vault.
That's a perfect way to describe it. Now, the vast majority of diamonds that people buy in jewelry stores, they form in the upper mantle, roughly 150 to 200 kilometers down.
Okay, so pretty shallow in the grand scheme of things.
Right. But there's a very rare subclass known as super deep diamonds. These account for maybe 1% of all diamonds ever mined.
Wow.
And the source material for this segment focuses on one specific staggering specimen.
Yes, I read this. This is a 1.5 carat gem quality diamond pulled out of the Karowe mine in Botswana.
Yes. And it's classified as a type IAB diamond.
Okay, let's stop there. Type IAB. What does that classification actually mean, and why should we even care?
It has to do with impurities. Most diamonds have tiny amounts of nitrogen trapped inside them. In a type Ia diamond, those nitrogen atoms are clustered together.
Okay.
The B designation means those nitrogen clusters have aggregated into very specific, larger groups of 4 nitrogen atoms surrounding a vacancy in the crystal lattice.
Why does the clustering matter, though?
Because nitrogen atoms don't just cluster like that overnight. To force them to migrate through the solid carbon lattice and group together into those specific B aggregates, it requires extreme heat and an immense amount of time.
Like how much time?
Often billions of years.
Oh, wow.
Yeah. Seeing that specific type IAB signature tells researchers immediately that this diamond is incredibly ancient, and it spent a massive amount of time soaking in the extreme thermal environment of the deep mantle.
Got it.
And when they analyzed it further, they realized it didn't just come from the standard 200-kilometer depth. This specific Botswana diamond formed exactly at the 660-kilometer boundary.
The absolute bottom floor of the transition zone.
Exactly.
It is literally a messenger from the deep. But, here's the procedural challenge that fascinates me.
What's that?
You have this priceless 1.5 carat super deep diamond. You know it has a microscopic speck of deep earth rock trapped inside its carbon vault. How do you analyze the rock without shattering the diamond?
Right. You can't just hit it with a hammer.
No. You would destroy the very pressure vessel that is keeping the inclusion intact.
To look inside without breaking it, geochemists use light.
Light.
Specifically, they use 2 non-destructive techniques on this diamond: confocal Raman spectroscopy and FTIR spectrometry.
Okay, break those down for me. How does Raman spectroscopy see inside a rock?
It's essentially a chemical barcode reader.
Okay, I like that.
They fire a highly focused monochromatic laser beam directly through the clear diamond and hit the tiny trapped inclusion inside.
Right.
Most of the laser light just passes straight through or scatters normally, but a tiny, tiny fraction of that light interacts with the chemical bonds of the trapped mineral.
And what happens then?
The energy from the laser causes those specific chemical bonds to vibrate.
Oh, like plucking a guitar string.
Exactly like that. And when those bonds vibrate, they absorb a tiny bit of the light's energy, which shifts the wavelength of the light that bounces back out.
Huh.
By measuring that microscopic shift in color, researchers get a unique optical fingerprint. Every single mineral vibrates differently, so the light tells them exactly what molecules are inside.
That is so cool. So they fire the laser into this Botswana diamond, read the bouncing light, and what barcode actually comes back?
It revealed what mineralogists call a polyphase inclusion.
Polyphase, meaning more than one.
Yes. It wasn't just a single uniform speck of rock trapped in the vault. It was a microscopic pocket containing 3 distinct minerals coexisting together:
Which ones?
ringwoodite, ferropericlase, and low-nickel enstatite.
Okay, let's unpack this combination because I know from the sources this is the real smoking gun. Why is this specific trio of minerals so important?
It all comes back to thermodynamic stability fields. Ringwoodite, as we've discussed, is the defining mineral of the lower transition zone.
Right, the 520 to 660 chunk.
Exactly. But the presence of enstatite is the real puzzle piece here. In this specific low-nickel chemical configuration, the enstatite is actually a retrogressed version of a completely different mineral called bridgmanite.
Retrogressed, meaning it used to be bridgmanite, but it reverted back to enstatite. Why would it do that?
Well, bridgmanite is the dominant, ultra-dense mineral of the lower mantle, which begins below 660 kilometers. It requires astronomical pressure to maintain its crystal structure. But when this diamond was violently blasted upwards to the surface in a volcanic eruption, a kimberlite pipe, the pressure dropped dramatically.
Because the carbon vault of the diamond is strong, but it isn't completely invincible. It couldn't maintain 23,000 bars of pressure all the way up to the surface.
Right. The pressure inside the inclusion dropped just enough that the bridgmanite could no longer hold its ultra-dense structure.
So it expanded.
It expanded, breaking its atomic bonds, and reorganized itself into enstatite, which is stable at lower pressures.
That is wild.
It's essentially a chemical fossil. The enstatite proves that bridgmanite was originally trapped in that space.
So if I'm tracking this, you have ringwoodite from above the 660 boundary and former bridgmanite from below the 660 boundary, literally touching each other inside this tiny diamond.
Yes. Finding those specific phases trapped together in equilibrium confirms absolutely that this inclusion was captured at the exact boundary layer where the transition zone ends and the lower mantle begins.
They nailed the location.
They did. They were able to pinpoint the exact capture conditions. 23.5 gigapascals of pressure and a temperature of 1,650 degrees Celsius.
Incredible.
It is a flawless physical snapshot of the 660-kilometer deep Earth.
That is just some CSI level geological detective work right there.
It really is.
But identifying the rocks wasn't even the blockbuster discovery of this paper, was it?
Not even close. The truly paradigm-shifting finding came from the second light technique, FTIR spectrometry, which uses infrared light.
Right.
When they analyzed the infrared signature of the ringwoodite trapped inside the diamond, they found water.
Water. Confirmed physically, 400 miles down.
Yes, and it wasn't just a trace anomaly either. The ringwoodite contained about 1.5% water by weight.
Wow.
They also found signatures of molecular hydrogen H2. This physical sample proved what the seismic hum had only hinted at. The transition zone at 660 kilometers is an incredibly wet environment.
Okay, here is where we definitely need to stop and clarify something crucial for everyone listening, because the terminology can be really misleading.
Very true.
When we say wet, or when articles talk about an underground ocean, we have to kill the Jules Verne journey to the center of the Earth myth right now.
Yes, please, let's do that. There are no hollow caverns filled with sloshing dark water down there.
Right.
There are no subterranean lakes where you could launch a submarine.
To analogize it, you should really think of the transition zone as a massive molecular sponge. Like, if you magically teleported a chunk of this deep ringwoodite into your hands right now, it wouldn't feel damp at all.
Not at all.
It would look and feel like a perfectly dry, solid rock. The water is not liquid. The hydrogen and oxygen atoms are physically baked into the crystal lattice of the mineral itself.
Exactly. They exist as hydroxyl ions trapped within the atomic structure.
Right.
But here's the math that makes this so astounding. Wadsleyite and ringwoodite have these very unique crystal architectures that are incredibly efficient at soaking up these hydroxyl ions.
How efficient?
Well, they can hold up to 1.5 to 3% of their weight in water. And the transition zone is a layer of rock 250 kilometers thick that wraps entirely around the sphere of the Earth.
That's a lot of rock.
It is. If you calculate the sheer volume of that layer and assume it holds even a fraction of the water concentration found in this Botswana diamond.
Oh, let's hear the number. How much water is realistically trapped down there?
The Mantle transition zone could theoretically hold up to 6 times the volume of all liquid oceans on the surface of the Earth combined.
6 times the Pacific, the Atlantic, the Indian Ocean, all combined. Stored inside the dry atomic structure of solid rock 400 miles beneath our feet.
Yeah.
That is almost incomprehensible.
It completely redefines our entire understanding of the planet's water cycle. And it raises a massive mechanical question.
Which is?
We know how the water gets down there. It gets carried down by the cold, subducting tectonic plates at the surface.
Right, the ocean plates absorb it.
The olivine in those sinking ocean plates absorbs water from the sea, gets dragged down, transforms into wadsleyite, then ringwoodite, pulling that water deeper and deeper.
Like a conveyor belt.
Exactly. But what happens when that sinking wet rock hits the 660-kilometer boundary?
Right, because we just established that at 660 kilometers, the pressure forces the ringwoodite to collapse into lower mantle bridgemanite.
And this is where the system hits a massive wall. Bridgemanite fundamentally hates water.
Really?
Yeah. Its crystal structure is incredibly tight and dense. It lacks the internal voids that ringwoodite has. Bridgemanite can only hold a microscopic fraction of water, maybe 100 to 2,000 parts per million.
Okay, so if I can use our sponge analogy again.
Please.
You have a sponge that is fully saturated with water. You drag it downward, and suddenly you crush the sponge so hard that the material itself fundamentally changes into a solid block of steel that cannot hold water.
Yes. It's what geophysicists call the ultimate hydrological trap.
The hydrological trap.
As the continuous conveyor belt of sinking tectonic plates pushes the wet ringwoodite down past the 660-kilometer boundary, it is forced to transform into bridgemanite.
And because it turns into steel, metaphorically.
Because the bridgemanite cannot hold the hydroxyl ions, it literally sweats out all that trapped water into the surrounding rock.
Oh, wow. But where does a massive amount of sweated out water actually go under that much pressure?
It migrates upward. And this initiates a process called dehydration melting.
Dehydration melting? What does that do?
In geology, when you inject water into hot, dry rock, it dramatically lowers the melting point of that rock.
Oh.
So as this water is squeezed out at the 660 boundary, it acts as a flux. It causes the surrounding mantle rock just above the boundary to physically melt into magma.
And because liquid magma is less dense than solid rock, it naturally becomes buoyant.
Exactly. It creates massive, buoyant, water-rich magma plumes that begin rising up through the mantle, eventually piercing the crust and fueling violent volcanic activity at the surface.
Let's step back and look at what this actually means for a second. The water cycle you learn about in elementary school, rain falls on the mountains, flows into the rivers, goes to the sea, and evaporates. That's only the surface skin of the true cycle.
It really is.
The real water cycle extends 400 miles into the earth. The oceans are being continuously dragged down by tectonic plates, squeezed out at a microscopic crystal boundary, and that squeezed water causes the deep melting that fuels surface volcanoes.
And then those volcanoes spew water vapor back into the atmosphere.
The deep, solid rock water cycle is directly driving surface geology.
It is a stunning closed-loop system of planetary life support.
It's beautiful, honestly.
But water isn't the only thing that gets rejected and hits a brick wall at the 660-kilometer boundary.
What else gets stuck?
The tectonic plates themselves get physically stuck there.
Wait, really?
Yes. This brings us to the dramatic geodynamics of the D660 boundary, what scientists refer to as the trapdoor.
The 660-kilometer trapdoor. Okay, I want to spend some real time on this because the physics here seem to operate in reverse compared to the boundaries we discussed earlier.
They absolutely do.
When olivine turned into wadsleyite, we spent a long time establishing that the transition was exothermic, meaning it released heat.
That's right, but the 660-kilometer boundary is a completely different beast. When ringwoodite breaks down into the lower mantle minerals, bridgemanite and ferropericlase, the phase transition is strongly endothermic.
Endothermic, meaning it absorbs heat from its surrounding environment.
Exactly.
So the thermodynamic engine completely flips. Why does it absorb heat instead of releasing it this time? I would assume crushing a rock even tighter would always generate heat.
It's a fair assumption, but it comes down to entropy and atomic packing limits.
Okay, unpack that.
By the time you reach 660 kilometers, the atoms are packed so tightly that to rearrange them into the even denser bridgemanite structure requires a huge input of energy just to break the existing bonds. It has to literally borrow thermal energy from its surroundings to force the transition to occur.
Okay, so it borrows heat. What does that mean for our Clapeyron slope?
Because it absorbs heat, it has a negative Clapeyron slope. This is the inverse of the 410 boundary.
All right.
A negative slope means that the transition requires more pressure, meaning greater depth, to occur if the environment is cold.
Okay, let's play this out with our sinking, cold tectonic slab again to see the mechanics.
Let's do it.
The slab is riding the gravity wave down. It's heavy, it's dense, it's sinking fast. It hits the 660-kilometer mark. The normal, warm mantle rock around it has plenty of ambient heat, so it happily borrows that heat and transitions into the ultra-dense bridgmanite.
Right. But the cold slab does not have that heat.
Because it's cold.
Because it is thousands of degrees colder than the surrounding rock, the thermodynamics stall out completely. The cold slab requires significantly more pressure to force the atomic change, so it cannot turn into bridgmanite at 660 kilometers.
It has to sink even deeper to find the pressure required.
Exactly. Which creates a bizarre physical scenario.
What kind of scenario?
Well, for a certain depth interval, you have a cold slab that is still made of the lighter mineral, ringwoodite, trying to plunge into a lower mantle that is already made of the much heavier, denser bridgmanite.
Oh, wow. And this is where buoyancy takes over.
Precisely. Because the cold slab is now chemically lighter than the dense rock it is trying to sink into, it creates a massive upward buoyancy force. The Earth is literally pushing back against the descending plate.
The visual that comes to mind is trying to push a giant, fully inflated beach ball underwater in a pool.
Yes.
Like you can push it down a few inches, maybe a foot, but the deeper you try to shove it, the harder the water pushes back against your hands, trying to violently force the beach ball back to the surface.
That is exactly the dynamic. The downward pull of gravity is suddenly fighting a massive upward push of buoyancy. And to compound the problem, it's not just a buoyancy issue.
What else is it?
The lower mantle is composed of completely different minerals that are mechanically much stiffer.
Huh.
The viscosity of the rock, its resistance to flow jumps by a factor of 10 to 100 times exactly at this boundary layer.
So it's not just like pushing a beach ball into water. It's like pushing a beach ball down, and suddenly the water turns into wet, thick cement.
Yes, and we know from high-resolution seismic data that this transition zone is staggeringly sharp.
How sharp?
The pressure interval required for this transformation is just 0.01 gigapascals. When you translate that pressure into physical space, it means the entire transition from the upper mantle to the lower mantle happens over a vertical thickness of just 250 meters.
250 meters. That is practically nothing on a planetary scale. You could walk that distance on a track in a couple of minutes.
You really could.
And that razor-thin line is the absolute boundary between the upper and lower halves of our planet's interior.
It is a phenomenal, highly resistant wall. So consider the fate of our cold tectonic slab. It's sinking at a few centimeters a year, and it slams into this 660-kilometer wall.
And the cement pushes back.
The buoyancy pushes up, the viscosity thickens, and the slab simply stops. It loses all of its downward momentum. It physically bends, it flattens out horizontally, and it just pools there, hovering on top of the lower mantle for tens of millions of years.
It just sits there, trapped. Which perfectly explains the Farallon slab graveyard we talked about earlier under the U.S. That ancient plate slid down, hit the 660 trapdoor, and just laid down to rest.
Exactly. That's exactly what happened. But here is the catastrophic catch. The tectonic engine at the surface doesn't stop. The subduction zone keeps churning. More and more of the slab keeps feeding down from the crust, piling up on top of this trapdoor.
It's like heavy, wet snow continuously piling up on a fragile roof.
A very apt metaphor. For millions upon millions of years, this immense cold mass accumulates in the transition zone. And as it sits there in the deep earth, it slowly begins to undergo thermal equilibration.
Meaning it starts to warm up.
Right, it begins stealing heat from the surrounding mantle.
And I assume as it warms up, the thermodynamic math finally begins to change, right? As it gains heat, it doesn't need as much extreme pressure to cross the threshold into bridgmanite.
Right. And eventually a critical tipping point is reached.
What happens?
The massive accumulated pile of slab warms just enough that the thermodynamic barrier completely breaks. The rock rapidly transitions into the ultra-dense lower mantle phase. The upward buoyancy resistance vanishes in an instant, and the entire piled-up mass crashes through the trapdoor all at once.
Oh, wow. Just a total collapse.
It plunges deep into the lower mantle in a sudden, catastrophic event known in geodynamics as a mantle avalanche.
A mantle avalanche.
Right there.
Millions of years of accumulated tectonic plates suddenly flushing down into the deep core. I have to imagine an avalanche of that scale has insane physical consequences for the surface of the Earth.
It is highly disruptive. These avalanches create massive transient downwellings that pull violently on the upper mantle and the crust. They completely reorganize global mantle flow patterns.
That sounds apocalyptic.
Many geologists actually believe these avalanche events are tied to major disruptions on the surface, potentially driving periods of extreme, widespread volcanism, or even triggering the breakup of supercontinents.
So When we look at the big picture of how our Earth operates, what does this trapdoor mean for the interior? I know the 2025 paper by Lissy and colleagues used a specific phrase for this. They called it intermittent layering of mantle convection.
Yes, that phrase perfectly encapsulates the dynamic. Because of this endothermic trapdoor at 660 kilometers, the upper mantle and the lower mantle do not mix smoothly or constantly.
Okay.
They aren't one big, happy blender circulating heat. Most of the time, they cycle semi-independently. The upper mantle churns on top, the lower mantle churns below, and the trapdoor acts as a strict barrier, keeping them mostly separated.
Until the snow gets too heavy, the roof collapses in a mantle avalanche, and the two layers are violently forced to mix for a brief geological period before the trapdoor shuts and seals them off again.
Exactly. This intermittent layering defines the rhythm of the modern Earth. It dictates the speed of plate tectonics, the cyclical chemistry of our volcanoes, the way heat escapes the core, everything.
But I want to key in on something you just said. You said it defines the modern Earth.
I did.
Our source deck takes us on one last trip, and this one is a time machine. Because if the 660 trapdoor is dictated entirely by heat and thermodynamics, what happens if we wind the clock back 3 or 4 billion years to the Archean Eon?
This is where geodynamics enters truly wild territory. During the Archean Eon, the Earth was in its infancy. It still retained a massive amount of its primordial heat generated from its violent formation and the constant bombardment of meteors.
Let's quantify that for a second. When we say a hotter Earth, how much hotter are we talking?
The mantle potential temperature back then was at least 200 Kelvin hotter than it is today.
Wow.
That means the average temperature of the deep mantle was exceeding 1800 Kelvin.
That is a radically different thermodynamic environment.
And that completely changes the rules of the game. We have these fascinating 2025 geodynamic convection models by researchers Renpeng Li, Julian Danberg, and their colleagues. They wanted to figure out what happened to mantle flow when the planetary engine was running that hot.
How do you even begin to model a planet that existed 4 billion years ago? You obviously can't use seismic noise for that.
No, definitely not. You have to use pure thermodynamic physics. They utilized an innovative entropy method paired with a highly complex computational thermodynamic framework called Hephaestus.
Hephaestus. That sounds like a Greek god of fire, which is surprisingly appropriate. But what exactly does that software do?
Rather than just guessing how hot fluid might swirl around in a sphere, Hephaestus calculates the exact thermodynamic stability of every single known mineral phase across a massive grid of pressures and temperatures.
Oh, wow.
It essentially asks the laws of physics. At 1800 Kelvin and 20 gigapascals, what is this specific mixture of atoms mathematically allowed to be? And their computational findings were shocking.
What did the physics say?
It said that in a hotter Archean mantle, the famous 660-kilometer trapdoor, the transition to bridgemanite that catches all our sinking slabs today, simply didn't happen.
Wait, it didn't exist. The boundary was just gone.
It was thermodynamically impossible. The ambient temperature was far too high for ringwoodite to exist in the first place, and the specific transition to bridgemanite could not occur at that depth. The primary barrier of the modern Earth was entirely absent.
So if the 660 trapdoor wasn't there to catch things, did the tectonic plates just fall straight through to the core?
Well, the tectonic plates themselves were vastly different back then, much hotter, thinner, and more pliable. Subduction, as we know it, might not have even existed.
Oh, interesting.
But the real story is what did exist in the deep Earth. Because while the 660 boundary vanished, the model showed that a completely different ancient phase transition took over the mid-manta.
A different crystal collapse. What was it?
Under those extreme Archean temperatures, wadsleyite didn't turn into ringwoodite. Instead, it transitioned directly into a mixture of garnet, specifically a high-pressure type called majorite and ferropericlase.
Okay, a massive garnet transition layer. Where exactly did this happen?
It occurred across a broad zone between 420 and 600 kilometers depth.
Let's run the thermodynamic checklist on this ancient garnet boundary then. Was this transition exothermic or endothermic?
Strongly endothermic.
Okay.
Just like the modern 660 boundary, this garnet transition absorbed heat from its surroundings, which means it had a negative Clapeyron slope. It acted as a thermodynamic barrier.
So it was another trapdoor. If it has a negative slope, it pushes back. Doesn't that just accomplish the exact same thing as the modern boundary?
It acted as a trapdoor, yes, but with a massive fundamental twist. Because it occurred at such high ambient temperatures, it didn't primarily interact with cold, sinking slabs coming down from the surface.
What did it interact with?
It interacted with hot, rising plumes coming up from the core.
Let me make sure I'm visualizing this correctly. We established that the modern 660 boundary acts as a floor. Cold slabs fall from the ceiling, hit the cold-resistant floor, and pile up.
Right.
You were telling me that 4 billion years ago, this ancient garnet boundary acted as a ceiling, trapping hot plumes rising from below.
That is exactly what the Lyell models demonstrate. Imagine a colossal, superheated plume of liquid magma rising from the core mantle boundary, carrying immense heat upward.
Okay.
As it rises, it hits this 600-kilometer garnet transition, and the thermodynamics flip on it.
Let me puzzle this out. If the boundary absorbs heat, it requires higher pressure for cold things. But a plume is hot, so it requires less pressure to transition, right?
Exactly.
Meaning the hot plume transitions at a deeper depth than the surrounding rock.
Exactly. The hot plume transitions into the less dense upper mantle phase earlier, which means, relative to the dense garnet rock surrounding it at that exact depth, the plume material suddenly becomes chemically heavier and denser.
So the hot plume loses its buoyancy.
Instantly. Its upward momentum just dies. It stalls out.
So you have these unimaginable pillars of heat rising from the deep core, trying to escape to the surface, and they just hit a brick wall at 600 kilometers and completely stop.
They couldn't break through the ceiling. So instead of rising, the hot plume material would spread horizontally. It pooled beneath the boundary, creating a massive, superheated stewing layer of rock between 500 and 650 kilometers depth.
Just a giant lake of heat.
It would just sit there, trapped, eventually spawning much smaller, weaker secondary plumes that would leak through to the surface.
That is a completely different operating system for a planet.
It created a highly stratified, layered convection style. The deep mantle churned with intense, unimaginable heat, but this ancient garnet ceiling acted as a thermal blanket.
Trapping it all in.
It insulated the lower mantle. It actively prevented the young planet from cooling efficiently, bottling the heat deep inside the Earth.
So how did we get from that bottled-up, superheated Archean Earth to the avalanche-prone, subducting modern Earth we have today?
Through a slow, inexorable process called secular cooling. Over billions of years, despite the insulating effect of the garnet ceiling, the Earth slowly, continually leaked its primordial heat out into the freezing vacuum of space.
Just a slow bleed.
Very, very gradually. The global average temperature of the mantle dropped.
And as the temperature dropped, the thermodynamics shifted again.
Exactly. As the mantle cooled and the potential temperature dropped below that critical 1800 Kelvin threshold, the thermodynamics of the deep Earth rewrote themselves. The wadsleyite to garnet transition stopped happening.
The ceiling just disappeared.
The ancient thermal ceiling simply dissolved.
And at the same time, because the temperature was finally low enough, the modern 660-kilometer Ringwoodite to bridgemanite trapdoor woke up and became active.
Yes. The secular cooling of the planet fundamentally changed which minerals were mathematically allowed to exist. Changing the stable minerals changed the phase transitions.
Right.
And changing those transitions completely rewired the physical convection style of the entire planet. The floor activated, the ceiling vanished, and this shift ultimately allowed the modern era of deep plate tectonics, subduction, and mantle avalanches to begin.
It is genuinely phenomenal to think about. The entire history, behavior, and evolution of our planet is dictated by the incredibly subtle physics of how crystals fold under pressure.
It truly is a masterclass in how the microscopic governs the macroscopic.
Well, let's pull all of this together because we've covered an unbelievable amount of ground today, or rather, underground.
A lot underground.
We started at the surface and dropped 400 miles down to a place where pressure crushes olivine into wadsleyite and ringwoodite. We learned how the heat released by that atomic collapse creates the gravitational pull that drives the tectonic plates we live on.
Yeah.
We saw how geophysicists mathematically filter the ambient hum of ocean waves and city traffic to map the ghost of the Farallon slab buried beneath the U.S.
And we looked inside a flawless Botswana diamond to find physical proof that those crushed crystals act as a molecular sponge, holding oceans worth of water that drives deep volcanic melting.
We stood at the 660-kilometer trapdoor, watching millions of years of tectonic plate pile up in a dense, stagnant pool until it crashes down into the core in a catastrophic mantle avalanche.
Just wild.
And finally, we used thermodynamic modeling to wind the clock back 4 billion years, seeing how a hotter Earth used a completely different mineral transition, a garnet ceiling, to trap heat and bottle up the deep mantle.
It's quite the journey.
I want to reinforce this one last time for you listening. The ground beneath you is not dead rock. It is not a static foundation. It is a hyperactive chemical and thermodynamic engine.
Absolutely.
It is continually churning, continually transforming, and it is directly making your surface existence possible by regulating volcanoes, storing water, and moving the very continents you stand on.
And that leaves us with a fascinating and perhaps somewhat provocative final thought to consider.
Okay, let's hear it.
We've just seen how Earth's secular cooling has already caused one massive shift in mantle dynamics, from an ancient garnet ceiling that trapped hot plumes to a modern bridgemanite floor that traps cold plates.
Right. The operating system updated when the temperature dropped.
But the Earth hasn't stopped cooling. It is still slowly losing its internal heat to space. So what happens a billion years from now?
Oh, wow.
When the average mantle temperature drops by another 100 or 200 degrees, will the thermodynamics shift a third time? Will the temperature drop so much that a completely new mineral phase transition takes over? One that is perhaps so strong and so thermodynamically resistant that it permanently locks the mantle in place and freezes plate tectonics and our deep water cycle forever.
That is a staggering thought. A planetary engine that gave us life, slowly cooling over eons until the crystals finally lock up for good. Next time you are walking outside, stop and look at a mundane rock on the ground. Think about the incredible, crushing, flowing, billions of years journey its atoms might have taken to get there. You will never look at a simple stone the same way again. Thanks for taking this deep dive with us. We'll see you on the next one.